Welcome back, ladies and gentlemen. Today's fun is absolute value and transformation graphing. We are going to kind of revisit this from 2.7, and it's not directly related to anything else. We're going to do it just kind of on its own so that you have this information in your brain for next year at pre-calc. So our whole entire point today is to be able to graph an absolute value function. By this point, we've been studying the function y equals x as a basic function. One thing you're going to need to know as you go into pre-calc and beyond is what we call parent graphs, what those parent graphs look like. And so this is the parent graph of a linear function. It's just the basic one slope of 1, y-intercept 0. And we're going to start with the same thing here. We're going to talk about the parent function and its associated graph for the absolute value graph. Now keep in mind that this is just fancy business for y equals absolute value of x. So when you go to graph an absolute value, if you think back to what absolute value means, if I go back old school and I'm going to plug in some numbers, the absolute value tells us how far something is from 0. So both -2 and +2 are 2 units from 0. So this is still a function. My y's repeat, but my x's do not. So when I go to graph this, I'm going to be plotting these points. And I end up, and I'm putting a lot of dots to help me hopefully make a straighter line. That still didn't work. And then this direction. So what I'm going to end up with is this V shape. So when you go to graph this, there's some significant features. I always think of what significant features can I pay attention to? Well, the first one is going to be the vertex, which is going to be right here, that point where it changes directions, and that vertex at the original parent graph is at 0, 0. Domain from left to right, so it goes forever to the left and forever to the right, and so we learned how to look at that and say, well, that's going from -infinity to +infinity, and it's not or equal to because you can't get to infinity or beyond, technically. So my range, which is my y's, this one is not unlimited. Because if you take a look at this graph, this entire bottom section, there's no graph there. So my range, meaning the part where I actually have graph showing from the y's, my lowest y is a 0, which it actually hits right here at the vertex. And then it goes to infinity. Well, transformations means moving around, changes. And so we're going to be changing this graph. And as we do so, the range will change and the domain will not. So this is going to be a lockdown. The domain for every absolute value graph will be from -infinity to infinity, otherwise known as all reals. But the range is potentially going to change as we transform the graph. So keep that in your brain. So from this day forward, you are going to know that the parent graph for an absolute value looks like that. What a big day. So let's talk about the changes that can take place. We like fancy words here in mathematics land. So we like the word translation. Translation is really a slide. It's going to be moving it left, right, up, down. So what moves it left? What moves it to the right? What moves it up? What moves it down? What translates it around? So there's a couple things you can think about. I always look at what's inside the bars and I think, okay, this might say plus or it might say minus, but this is actually going to go the opposite direction of what I think. So in this case, if I have a plus inside here, it's actually going to shift my graph to the left. If I have a minus h inside here, it's actually moving my graph that far to the right. Looking at the number that's outside of the absolute value bars, I always call it the container. So the number inside the container goes the opposite of what you would expect. But out here, you get what you get. A positive k is going to move the graph up k units. A negative k is going to move the graph down k units. So as you're translating it around, you're going to be moving the vertex. Because if I took this graph and moved it up, down, left, right, the vertex is the key point and that's going to be moving. So we're going to take a look at how those movements change our vertex when we put it all together. The other thing that can happen is called a dilation. And again, that's fancy term. It's basically a stretch or a vertical shrink. I sort of think of this, to be quite honest, I think of this, and it's not technically what this is, but this A value is, and I'm putting that in quotes, the slope, but only of the right side. So if I have a 1 there, like I do up here, because currently there's nothing in front, which is a 1, my slope is up 1 over 1, up 1 over 1, up 1 over 1. And then I know that my graph mirrors itself, so up 1, back 1, up 1, back 1, up 1, back 1 would allow me to fill in the left side with that type of thinking. So I'm looking at the value of that A. As A is greater than 1, so say for example a 2. Think about what that's going to do. If I were to go back to this graph and instead of going up 1 over 1, I was going to go from my vertex up 2 over 1, up 2 over 1, up 2 over 1, and then connect it. Up 2, back 1, up 2, back 1, up 2, back 1, and then connect it. You can see that 2 times the absolute value of x has a different look than our original absolute value of x with an A value of 1. So what this is going to do, this is going to stretch vertically. It's going to make it taller, steeper, skinnier, however you kind of think about that. What if I had an A value where the absolute value of it was less than 1? So say for example, let's make it easy. I had a 1/2. So if I went back to my graph and I wanted to see what would that do, if I'm thinking of that as the slope of the right side from the vertex, I'd go up 1 over 2, up 1 over 2, up 1 over 2. Then I would mirror that going the other way, and I won't torture you with me counting. And then if I look at that graph and I say, okay, this is the 1/2 absolute value of x graph. How is that different than my purple one, which is the original? Well, this one is wider. So I always think of this as being wider. I think of this other one as being narrow. The technical term is a vertical stretch as it gets taller, or we call it a vertical compression or shrink. Again, that's just terminology. So it shrinks vertically or it's vertically compressed, meaning it's kind of pushed down further, gets wider. But again, if I always kind of think of that A value as the slope of the right side of my graph, that's going to really help me when I'm trying to graph these on my own and acknowledge the changes. So this one's crossed off. But if you think about it, putting in a negative inside of here, this is going to turn into a positive x as it comes out of there. And right now, that's going to be a type of reflection we aren't worried about. This, however, with the negative on the outside, this is the equivalent, again, with our fancy notation of that. Think about your experience in graphing. When there's a negative out in front, think about what happens to the graph. If your brain right now is empty and you can't think of anything, let's think about what the A value is in this scenario. It's -1. So if I use my previous methodology of thinking of that as the slope of the right side, then I would start at my vertex and I would go down 1 over 1, down 1 over 1, and so on, because that would have a slope on the right side of -1, because that is the A value. Then I need to mirror that on the other side as well because it is symmetrical. And so it seems that the difference is obvious in the pink graph compared to the others. And that is what happens in every type of equation when we have a negative in front. It flips over, or it's upside down, or technically we say it is reflected over the x-axis. So the queen bee equation. Okay, see, Miss Meyer is so cute. She has this little queen bee for you. So this is the big one where it's all put together. And I will say that when I think about this, I kind of think about these might look at pluses or minuses. The reason this one's a negative, if you remember, is we always use the opposite of that. So when I'm looking at my vertex, think about this again. Excuse me. Positive h moves it to the left. A negative h moves my graph to the right. Those are going to impact my x coordinate, and they're going in the opposite direction. So we put here negative h. That always scares me because people think it always has to be negative. So think of it as the opposite, because if you have in here, for example, x minus 2, the opposite of that is going to be a positive 2. So what you see as the x coordinate in your vertex will be the opposite number of what you see inside the container, the bars. K is easy peasy because it's on the outside. Positive k goes up, negative k goes down. So then your y value will just be that k value. So what I like to do when I'm graphing these is I like to start at the vertex, and then I like to use A to help me get the sides the way that I need them to be. So let's do a few examples. In this first one, I have a -1 here and a +3 here. So if I look at that, that's going to be shifting to the right. I'm just kind of thinking like, what's going to happen? This is going to go to the right 1, and it's going to go up 3. So I want to know that and kind of think about that. So when I'm done, I can look and see if that's what my graph looks like. The vertex I just learned, I need to take the opposite of what I see, so +1, and then use this number, the k value, as is. So my graph is going to have the vertex at 1, 1, 2, 3. I already know my domain because it is always, 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 always all real numbers written in our fancy new way. Range, however, I like to graph it first and then take a look at the range. If I look at this graph out in front, I don't have anything. And what that's telling me is that my A value is 1. So I'm going to have just an average run-of-the-mill normal sized absolute value graph. But what I use that as again is my slope from this vertex. Up 1, over 1, up 1, over 1, up 1, over 1 for my right side. And then I mirror that on the left side. And that, my friends, is the graph of that particular function. And now I can look and say, okay, my range, I don't need any of this. I only need from this lowest point of 3, which is included, up until infinity. Did I include that back in my very beginning? I sure hope so. Yes, go me. And then comparing it to this is simply talking about those transformations to say, this shifted to the left 1, except for not. It shifted to the right 1. And it shifted up 3. And if I look at it, I can see that because my normal origin would have been right here, my vertex, and it's clearly right 1, up 3. So I feel good about my final graph. All right, so I would say try this one on your own and then look to see what I'm doing. I'm going to think first about what happens because of this. Then I'm going to think about what happens because of that. I'm going to fill this in because that's always the same, and I love always in math because I don't get that very often. I'm going to think, okay, I need to use the opposite of this part for my x. And I need to use this one as is for my y. And I'm going to leave my range until I graph it. And then I like to think, what is the A value? So I look out in front, and with nothing there, my A value is going to be 1. So no stretch, no shrink, no flipping over. I'm good to go. So I go to -2, -4, plot my vertex, and then I use my A equals 1 to draw my right side and mirror it on the left. This is so easy peasy. You guys are going to be so awesome at this. Oh, I have to do my range. So I look again and think, what don't I need? I don't need this part down here. There's no graph down there. I only need from this point on up, which is located at -4. That's included in the graph, and it goes up forever from there. All right, just when you think you know what you're doing, something weird happens. So make it less weird. This is not how we've written them. We just had y alone. So I'm going to take that 3 away to the other side, And I'm really looking at y equals the absolute value of x minus 3. Still a little weird. Think about the changes. Well, the only thing that changes in this case is that there's a minus 3 at the end. So that's going to move my graph down 3. It's not moving left. It's not moving to the right. It's not stretching. It's not shrinking. It's not flipping because my a value is 1. So when you go to the vertex, this is going to be a minus 3 because we always use that as is. Here I'm supposed to put whatever was in with the x. Well, there's nothing in with the x, so my x coordinate is a 0. Oh, I'm going to get this one right because that's always the same. All right then. So at 0, -3, put myself a big bad dot for a vertex. Again, my a value is 1, so I use it as the slope on the right side to determine my steepness, and I copy that on the left. Copy that. Get it? Okay. So now I can determine my range. I can think, all right, I don't need any of these y's down here. I need from this point on up, which is from -3 on up. Okay. Oh my goodness, we have so many. So let's see. Yeah, we'll do a couple more. You can stop when you need to or skip ahead. Here, the obvious change is the a value. There, if you look at it, there's nothing in here with the x and nothing at the end. So there hasn't been a translation. The only thing we have had is a vertical stretch of 3. So my vertex is going to stay at 0, 0 because it hasn't moved left, right, up, or down. Pretty sure my domain is going to be the same because it's always the same. And then according to this, if I'm thinking of my a value as the slope of my right side, I'll count up 3 over 1, up 3 over 1, and I'll get the right side. Copying that same pattern in a mirror fashion, I get the left side. And I'm not surprised to find that I have a absolute value graph that's tall and skinny because I was expecting a vertical stretch. It's 3 times steeper than the normal. Now for my range, I don't need any of this down here. So I'm looking at anything from 0 on up. Okay, a doozy. Here we go. It's got all the good parts. Let's do this. I think I'm going to get a different pen just because it's so fun. So let's take it one thing at a time. One thing that I see is it's going to go up 1. The next thing that I see is that it's going to go to the right. Don't be fooled by that negative, 3 units. Then I see a 2, so it's going to be vertically stretched because 2 is bigger than 1. And it's going to be inverted, flipped, reflected, whatever term you like. It makes you feel the most fancy. I'm also just kind of putting in my brain that the number out in front as my a value is a -2, so that when I go to graph, I can make my life easy. Vertex, still the same process. I look and say I need the opposite of what's in here as my x, and I'm using this number as is for my y. Domain, basically free points. So there we go. So I'm at 3, 1, and now I've taken care of my shifting. I took care of that. I took care of that. Now I'm going to take care of these 2 in one fell swoop because I'm going to be thinking the slope of my right side's -2. So from this vertex, I'm going down 2 over 1, down 2 over 1, down 2 over 1. And then I'm copying that pattern in a mirror fashion for the left side. Wow, that's like the world's worst line. But when I'm done, I'm pretty happy because it's flipped over, it's skinnier than normal, it's moved to the right 3, up 1, I'm good to go. And now I have to think really hard about my range because it's the top part I don't need. So here I'd have to say, what's the lowest it goes? Well, -infinity. What is the highest it goes? Right here, which is 1. That's a thinker. The grand finale, here we go. Try this one by yourself, then turn the video back on and see if you get it right. Wouldn't that be smart? going through, writing down what I see happening. I've got this happening. I've got this happening. Ooh, that's less than 1. So I'm going to have a vertical shrink, compression. It's going to be wider. Whatever way you want to think about that. My vertex. How do I do that? I take the opposite of this bad boy. Take this guy as is. My domain, I can do with my eyes closed. Okay, technically my eyes are not closed because I wouldn't be able to write. And now I'm going to graph it before I do my range. So I'm going to bring myself over here as a start point, and then I'm going to think about my 2/3 A value as the slope of the right side. Up 2 over 3. Up 2 over 3. Up to back 3 to mirror that on the other side. And of course I'm going to go off the page because that's how things work for me. But I check it off when I'm done. I say, all right, is it 4 to the left? Yes. 2 down? Yes. Is it wider than normal? Yes. Great. Alrighty, friends. So go ahead and try that 2-7 worksheet and then look through the assignment also. And you're going to do your IXL. And again, at the IXL, you're going to be aiming for a score of 80 or over. So if you get a 76, then you're going to be looking at 7.6 out of 8. If you're feeling like this is easy peasy lemon squeezy and you want to go for 100, then you can get 10 out of 8. So you have those 2 fun things to do to practice what you just learned. If you need to look at the video again, go for it. If you want to sit down Saturday